I think Buffon mentioned that he's interested to look at hydrogen produced from bio anaerobic biodegradation, biodigestion, which I will address in the biogas lecture, as Flavio also suggested last one. Anything else? Okay, so I'm going to start. So this lecture, we're going to go through the type of energy storage and how hydrogen fits on these energy storage types. I'm going to talk about the oil and gas industry and the threats from batteries. I'm going to talk about hydrogen versus battery cars, hydrogen production pathways, the world experience for hydrogen, and some proposals for Brazil hydrogen production and export. So around 50 to 60% of this lecture I have already addressed in some of the seminars that I presented, but it's interesting for the students that haven't listened to these lectures, just because to give an overview of the current state of hydrogen, because hydrogen has always been the technology of the future, and there were um, several periods, for example, 2010, or early 2000s, that people mentioned about hydrogen and hydrogen becoming a reality, but the market is showing that now is the time where hydrogen will have its largest challenge and to become actually reality. And probably we're going to have hydrogen in 10 years' time, and it's going to be a viable alternative. And I'm going to explain the reasons for that. So, comparing to the different types of energy storage, we have the hydrogen is close to pumped storage, as we presented the last lecture, as a very high energy storage potential. Of course, it has a lot of power. You can produce a lot of power with hydrogen. For example, you have a sports car that you get a lot of speed very quickly with fuel cells and drive very fast. But also, you can store hydrogen in salt domes under the ground. You can liquefy and store in tanks. Of course, you have some evaporation, because the hydrogen has to be kept at very low temperatures, minus 253. But as the hydrogen evaporates, you can use the hydrogen produced from the evaporation, for example, to operate a generator and generate electricity for the plant. And you can use it for cooling. You can use it for several other means. So now I'm going to talk about the current trend of hydrogen and why a lot of people are paying attention to hydrogen. So one of the reasons is oil and gas industry has not been very interested in investing in hydrogen for the never. It has never been interested in investing in sustainable energies, because it's always thought that people would need oil, and oil will supply the world, and if you stop producing oil, what's going to happen is that people are going to starve. You're going to have lack of food and a lot of problems with developing nations and developed nations. And this is true, right? We need a source of energy in order to supply our energy needs. Hello, hello. So what happened is that after the COVID crisis, the price of oil reduced so much that the oil and gas companies are more reluctant now in investing money in oil, because they're going to put a lot of money in investing in oil extraction, exploration, in refineries, and all these assets which are very costly, very expensive. You need a lot of subsidies from the government. But if oil prices are $30 per barrel, $40 per barrel, the returns are very small, and so they might as well invest in something new and start it. This is the time to invest in something new. Why? Because all countries in the world are having the lowest interest rates. All US, Brazil, Europe, China, Japan, most countries, even developed, underdeveloped countries, they lower a lot their interest rates. So what happens that money is very cheap now to invest in hydrogen, in batteries, and things. And countries are constantly printing money, so money is not the issue now. The countries just want to make sure that they invest in the technologies that are going to be the reality, the technologies that give them a return for their investment in the future. So after COVID, oil prices fell down, and a lot of oil companies started investing in hydrogen. The main reason why this is happening is because of the rapid increase in battery cars around the world. The transport sector, road sector, cargo sector, it consumes around 30 to 50% of the energy in developed countries, developing countries, sorry. And there's a big push in order to electrify the transport sector. But the thing is that hydrogen, so if you have a hydrogen industry, you still need to liquefy the hydrogen, to transport the hydrogen in pipelines. You need to distribute the hydrogen in petrol stations. While on the other hand, battery cars, you just need a plug in your house or in your job, and then you charge the battery from your car, and you don't need even a petrol station. So batteries are going to be very good for the electric sector. So electric sector will have 30%, 40% more customers to sell electricity. But on the other hand, the oil and gas sector will have fewer customers in order to sell their oil products. This is the market capital of Tesla today. I always update this graph when I present this graph, and it keeps growing, the difference. For example, Tesla shares are worth around $500, and if you sum the 6 next ones, so Volkswagen, Toyota, BYD, NIO, Daimler, and General Motors, then you have the market capital of Tesla. So Tesla has a lot of money. They have a lot of power with this money. They can change policies. They can build cheaper cars because they just have a lot of money. A lot of people are trusting in the company and investing in the company. And on the other hand, for example, the oil companies, for example, ExxonMobil, shares of ExxonMobil is around $38, which is equivalent. I removed the numbers here. Sorry, but this is 2017, 18. So prior to that big crisis in 2008. Sorry. Hold on. Let's have a look. Shell markets. Shell. ExxonMobil. Yeah, so this was 2008. So the level that we are today is equivalent to 2002. So the shares, if you bought a share in 2002 thinking that you go up, it went down. At least you didn't lose money, but you could have sold on the way. So what I'm saying is that the value of ExxonMobil is the same as 2002, which is not great for the oil and gas company. And so continuing, the reason is a lot of electric cars going into the market. For example, 2018, you have the China sold around 4.5% of cars, electric cars, US 2.4, and several other countries increasing exponentially the amount of cars that they sell. The UK, Australia, Norway, and several other countries have passed laws that after 2030, there will be no more ICE cars, no more internal combustion engine cars sold in these countries. And the number is increasing. A lot of countries are not going to sell oil, fossil fuel cars anymore. It has to be either batteries or hydrogen, which is the future, right? But it will have a lot of impacts in every country in the world. So battery infrastructure requirements, you just need a plug-in. You don't even need to change the oil because you don't have a internal combustion engine. The engines are much simpler. So maintenance cost is much smaller. The complexity is much smaller. You don't have pollution. It's just electric. It's just. And as I showed you prior in the first lecture, who is going to benefit a lot from this is the electric sector. So electric sector is going to make a lot of money. They're going to have to have a lot of jobs. They're going to have to increase their generation capacity, increase money investment in distribution, for example. The battery cars could even help with distribution because it can store energy, for example, at night when people are not driving and you have the distribution system sleeping, so it's not being used. Usually the transformers, they blow up around 4 or 5 in the afternoon, 7, when the demand is very high, and then they can't sustain the charge, and then they explode. So at night, transformer only explode if there are very high winds, thunderstorms, and things like this. Not really due to capacity of the transmission line, the distribution line, but more due to physical constraints. And on the other hand, a hydrogen supply future would look very similar to a gas, for example, natural gas industry, not so much with oil industry, but natural gas industry. You need pipelines, you need storage tanks, you need petrol stations, you need refineries, you need pretty much all the infrastructure that an oil and gas company has. And the other problem is that, for example, if you don't need more of this infrastructure, so this is for hydrogen, but if, for example, you don't need more infrastructure for gas, what happens at the petrol stations, they will have to shut down and the location will not be worth anymore because you won't sell to another petrol, oil and gas industry. You have to decommission all your pipelines. You have to lay off people, which costs money also, and you have to go bankrupt. One of the options to go bankrupt and ask the government to pay the bill.
Julia.
Hi there.
Could you? I can't see. Oh, okay. The slides. Okay.
Sorry.
Thank you.
Thank you. Yeah. So comparing hydrogen, natural gas with gasoline, diesel, ammonia, batteries. You have, this graph is very good in order to compare these different fuels. So hydrogen is the one that's the lightest. So this, it contains 142 megajoules per kilogram. High heat power. So high heat power assumes that after you burn hydrogen, you still manage to convert the steam that you produce into water. So you also take the heat from the steam to condense the steam and put it back at 25 degrees. So low heat. So the energy density of hydrogen, low heat, low heat value is around 120 megawatts per kilogram. And the other ones also have a similar adjustments. We in Brazil, in Europe, we usually use low heat value. In the US, they usually use high heat value. I'm not sure if you're aware of this terminology. If you want me to better explain, let me know. So yes, hydrogen is around 3 times, carries around 3 times more energy than natural gas by weight. On the other hand, you need a volume twice as big in order to carry the same amount of energy. So you need twice the amount of volume if you are carrying liquid hydrogen. If you're carrying hydrogen gas at 500 bar, it's around 30 times larger the volume compared to compressed natural gas, which is usually at 250 bar. And gas, the normal gas it occupies a similar not similar volume, something like, without pressure, it's something like 5 to 6 times more volume hydrogen takes than natural gas by volume. Yeah, so the other very interesting aspect is that batteries, they store something like 100 kilojoules per kilogram, or 200 kilojoules per kilogram. So it's, if you have one in this line, it's 10 times more than one. And in this, we can conclude that batteries are very heavy. They're not very they have very low energy density. So it takes a lot of energy in order to carry the batteries themselves, which is the major drawback of using batteries for transportation, for example, because you need to carry the battery. So comparing hydrogen with battery cars, we have the hydrogen. It's so hydrogen carries 40,000 watt hour, which is a different measurement than megajoules per kilogram, or 250 watt hour per kilogram. It's something around 50 times smaller. However, batteries have a big advantage due to the fact that did I show you this slide already, by the way, in the first lecture?
I don't think so.
No, I don't remember.
Okay.
It's the first time, I think.
Thanks. Batteries have an overall efficiency around 85%. You just need to transform the electricity from your house, which is at alternate current, into DC, which you lose 5%, something like this. You charge the battery, which within the battery you lose around 5 to 10% also. And then in order to provide high power with a motor which is light, you also need to turn the current back to AC, and you also lose something like 3 to 5% in this conversion. But it's overall a very efficient energy storage approach. On the other hand, hydrogen is a very expensive fuel, mainly because if you want to generate hydrogen from electricity, for example, with electrolysis is something like 60 to 70% efficient. You have to compress the hydrogen. I mean, depends on the technology. For example, there are technologies which are very expensive. For example, the electrolysis, those big batch tanks where you have the anode and cathode, and you can reach 80 to 90% efficiency. But if you want to produce electrolysis, that is not so expensive, it's cheaper, it's lighter, and you can vary the amount of hydrogen that you produce, storing energy from the grid. So when you have a lot of wind power, you store more. When you have less, store less. So with a lower capacity factor, then the efficiency reduces to 70, 60. You have to compress. For example, compressing hydrogen to 700 bar, you lose something like 10 to 15% of the energy within the hydrogen. If you liquefy hydrogen, you lose around 30%, 30 to 35%. So just to manage hydrogen, in order to be able to use the hydrogen with a smaller volume, you have to invest a lot of money, you lose a lot of energy, it's very inefficient. And then the fuel cells themselves, so fuel cells, they can be up to 60, 50, 40% efficient, but usually for very high performance cars, so cars that you want to go very fast, very quickly, so a lot of power, usually the efficiency from these fuel cells are around 40%. People say about 70% fuel cells. Yeah, there are, but not usually for cars. So if you want to accelerate very quickly and you want a lot of performance with a light fuel cell, the efficiency is smaller. And then after, you also have to transfer from DC, because fuel cells generate electricity at direct current. You have to change to AC current. So here they're saying 34% efficiency. It could be 30, it could be 20. I think 40, maybe. It will depend a lot on the amount of money they invest, on how good your system is. But overall, it's not very energy efficient. It would only make sense if you have a lot of solar powers everywhere and wind powers producing very cheap energy, which you can just waste it because your hydrogen industry is inefficient. So compared with the weight, the amount of weight the car has, the range. So usually people talk about battery cars have a range of 600, 400 kilometers. And then if you want a bigger range, you would have to go for hydrogen, because batteries take a long time to recharge. When you're fully charged, you usually wouldn't go as far as 300, 400 kilometers. Only if you drive very slowly and you save a lot of energy and try to, make sure you make the best of the energy that you have in your battery. But for a hydrogen fuel cell, you can go 1,000 kilometers, 2,000 kilometers without refueling, depending on the size of your tank. But overall, in order to take into account this inefficiency, the cost of hydrogen, it makes sense to use battery cars. If you, for example, going to drive 50 kilometers per day, if you're going to maximum 100 kilometers, so this is the maximum you can drive with batteries. But the point where hydrogen is competitive with battery cars is something in between, like something like 100 kilometers. So if you only drive 50 kilometers, then batteries are definitely better for you if you just use to drive in your city. But for example, if you're a taxi driver that drives 300, 400 kilometers per day, then you need hydrogen car. Another issue for cargo transportation is that a lot of the weight that you will be carrying if you have a battery truck, is the weight of the battery itself. And this has an impact on, for example, the street that you're driving, because your truck is going to be more heavy. So you're gonna have to invest more money in your streets in order to avoid having holes and destroying your highways. On the other hand, if you have hydrogen cars, then of course you can still destroy the highway, but you'll be less likely, because at least you don't need to carry all the load from the battery. Another very interesting aspect is efficiency, right? So when you're using fuel cells instead of ICE, internal combustion engines, you have that the Carnot cycle increases with the temperature, but of course you can't use the motors with too high temperature, because then you produce a lot of NOx, which causes acid rain and problems with health problems in the city. On the other hand, fuel cells, they actually reduce the efficiency with the temperature. Not sure if this slide was in the right location, because fuel cells for transportation are not so efficient like this. But this is an interesting graph just to show that fuel cells is the opposite. The higher the temperature, the lower the efficiency. Of course, internal combustion engines, the higher the temperature difference between the ambient and your car, the higher the efficiency. So, for example, there are fuel cells that you have 70, 80% efficient. And for example, you can use these fuel cells for cruise ships, shipping, so those big container ships, trains. So this type of transportation, which you don't need to accelerate and brake very quickly, or very large size, for example, waterways, so those transport in rivers, these type of transportations that you just turn on the motor and you go. For example, even airplanes. So you have an airplane and you're using a fuel cell. Also, very high efficiency. Why? Because you're using it at maximum capacity for example, 6 hours, 7 hours. And for planes, it's very convenient to have a very efficient mode of energy production, because you need less fuel. And if you need less fuel, you need to carry less weight in your plane, and carrying cargo in a plane is very expensive. So hydrogen, even this graph, is very convenient for airplanes. They'll have to change a little bit the design, because now the fuel is only it's stored in the wings of the plane, because the volume is very high. So it stores a lot of energy in the small volume that they have inside the airplane. But they will have to create new designs for planes in order to increase the volume of the plane, overall volume of the plane, and then be able to store hydrogen. but the hydrogen that you use is much lighter, and you need less hydrogen because the efficiency is around 60 to 70% in planes. Is that clear, more or less? So,
just a question, Julian.
Yeah.
In planes, they will burn the hydrogen, or by combustion. It's not the same system as a cell, right?
Yeah, exactly. So, for example, you have rockets. Rockets, they work with hydrogen and oxygen. They carry liquid hydrogen, liquid oxygen, and they burn it. Problem with this burning hydrogen is that you need to carry the oxygen with you, and the airplanes don't really have volume enough to carry all the oxygen with you, because if you burn hydrogen with air, you will reach very high temperatures burning, and the problem is that you produce a lot of NOxes, so hydrogen oxide, and with a very busy industry, airplane industry, you cause acid rain, and you have impact to the cities. So of course there is a possibility of burning the hydrogen, but most of the proposed airplane prototypes, they use those propellers because they use fuel cells. The advantages of fuel cells is because they're more efficient. However, you cannot fly so high because you need a propeller, and the propeller depends on how much air you have. So go too high, the pressure is very low, which the propellers, they don't operate very efficiently. So it's an optimization issue. There are people actually building hydrogen with propellers, with fuel cells. There are people building airplanes with combustion engines. However, if you build a combustion engine that runs with hydrogen, you have to be very careful with the temperature of the ignition in order to reduce as much as possible the production of NOxes. Nitrogen is in the air and reacts with oxygen, producing NOxes, and if it builds up in the atmosphere, you have acid rain.
All right, thank you.
But you probably understand this more than me. Maybe I'm saying something wrong. Do you?
Yeah,
Can you correct me? Maybe if I'm wrong.
This is right. We had the discipline combustion last semester, and this is exactly right. The temperature, if the temperature is too high there, because of the nitrogen, we will have all this nitrogen oxides and so forth and so on. But do you believe that the batteries will improve the situation that we have right now? I mean, energy per weight. Do you believe in more breakthroughs that will improve? Like, they need like 20 times more to be competitive technically. Do you believe in breakthroughs in the battery area?
So battery with metals. I think it's difficult because, for example, lithium is the lightest material on Earth, but of course you can change the approach in order to reduce the weight of the cathode anode, the membrane, the whole system. But there is a theoretical limit to this, to how light you can travel with battery. I'm not sure what's this limit, but for example, since the beginning of Tesla, for example, Tesla used to be 100 watts per hour. Now, the lightest batteries are 250. Maybe you reach something like 1,000 watts per hour per kilogram. I have no idea. So I'm just chuta do valor aqui. I have no idea. But yes, I'll look at this in the battery lesson. Very good
Perfect.
question to I'll have a look.
All right. All right.
Thanks. But for example, this graph shows that battery planes will be very difficult to be feasible because if you can see batteries and hydrogen, the differences are huge. And in a plane, weight is very important. So I think it's going to be very difficult to see in the future battery planes. There's another question. There's another thing that, for example, nowadays people are developing hydrogen batteries, which is what is a hydrogen battery? A hydrogen battery is literally, for example, there are nowadays cell phones which run on hydrogen, but you don't fill up in hydrogen. You have your phone, which has a little bit bigger storage battery, and once you plug in, you have two storage vessels inside the cell phone, which turn the oxygen, no, the water. So you have a little bit of water, which is separated in hydrogen and oxygen, pressurized, high pressure. Hydrogen and oxygen. And then when you unplug and you want to use your phone, what happens is that the phone turns the hydrogen and the oxygen into water, and you use your phone. So it's similar to a battery, but it's a hydrogen battery. It's not the metal battery, for example. Do you understand all that? For example, the U.S. Navy, the U.S. Military forces, they have a lot of equipment. Army, yeah, thank you. They have a lot of equipment, and carrying batteries in order to operate these equipment is very expensive. So they're investing a lot of money in hydrogen batteries, as they are 10 times lighter than metal batteries. It's literally they have a electrolysis device, which also work as a fuel cell. So they're usually called reverse fuel cells. So the same device can be used for producing hydrogen and using hydrogen to produce electricity. And the only thing that's missing is electricity. So you put electricity in the system, it turns hydrogen and oxygen into water. No, sorry. You put electricity in the system, it turns water into hydrogen and water and oxygen. And then you have the hydrogen and oxygen. And then you pass through the fuel cell, you generate electricity and water. So maybe in the future, we'll all be using hydrogen batteries also. They're lighter. I'm not sure. Maybe the lithium batteries, they are more convenient for example, if you use your phone for 6 hours. But if you wanna a solution that you have energy storage for 3 days, 4 days, 5 days. For example, you go to war and you don't have time to charge your phone, and then you have a hydrogen phone that lasts for 5 days.
This is interesting. I'll Google if I find one smartphone. I saw one right now. It's called Red Hydrogen One, the name of the smartphone. I don't know if this one.
Did you see in Amazon or?
Right now, I found it for $1,200, but I don't know if this one a little bit too much for me.
Yeah. So the only difference is that the battery lasts longer. I wasn't sure about this. I thought it was still in research. I thought it was still in research stage, but so yeah, they're selling hydrogen phones now. incredible. Those fuel cell types. You have two main fuel cell types, and these is proton exchange membrane cell and the solid oxide fuel cell. The main difference between them is that in the proton exchange membrane cell, the atom that passes through the electrode is hydrogen, protons. Not hydrogen because it's just hydrogen ion, the proton. It passes through the membrane, and the electron of this hydrogen goes through the electric system, and then you can use this current or electricity generation, and then when it comes from the cathode to the anode, you have that it combines into oxygen molecules and turns into water. So this is the proton exchange membrane. The anode is usually platinum. It's very expensive. And the electrode, I'm not sure about the anode. I didn't put it here, but it might be something cheap like copper. The electrode is this membrane here. Is a polymeric membrane, so plastic. Solid oxide fuel cell is the other type, which instead of passing hydrogen, the oxygen passes through the electrolyte. And for the hydrogen, it is the fuel, you put air in, and only the oxygen passes through. This oxide fuel cell is very convenient. For example, if you want to extract the water out of this fuel cell, for example, you are in a very dry place, you want to generate electricity, you want to generate water for drinking, for something in the desert, you just need to condense the water. You don't need to cool down the air also, because usually when you burn something in an engine, you produce CO2, water, and nitrogen. But nitrogen is 70% of the output. This water is convenient. Why? Because you can put in a tank. Tank is going to increase a little bit of pressure, but it's going to cool down. You don't need to have an output air stream. The only output is water from this tank, so reduces substantially the investments that you have in order to condense this water. This oxide fuel cell also works with, for example, methane. It works with gasoline, diesel. It doesn't work with coal. It has to be liquefied. So how does it work? This oxide fuel cells, they are really hot. They are around 700 to 800 degrees. And when the fuel reaches this fuel cell, you have pyrolysis happening here, and you produce hydrogen. Is similar to a steam reforming. So you put inside the fuel and water, steam, and then you produce hydrogen because the fuel cell is really hot. And then you produce the outputs of this process is water and CO2. Another great advantage of this fuel cell is the fact that you produce CO2 separated from the air. So you only produce CO2 and water. So if you condense the water, you only have CO2, which you can then store under the ground and in a carbon capture storage way. In Norway, they have, it's becoming very famous. And nowadays, people don't have a boiler. So they don't use a boiler in their houses in Norway anymore. They use solid oxide fuel cell. Why they use solid oxide fuel cells? Because they have natural gas coming from the grid, and then they put this natural gas in a solid oxide fuel cell, and then they produce electricity at an efficiency of 50%, 60% efficiency, and they usually sell the electricity to the grid because what they want is the heat. Why? Because as you produce water, you can extract the heat from the steam much easier and much less cost because you don't have to cool down the nitrogen. Just cool down the water, which is convenient. And so these systems has an efficiency, overall efficiency of 90%. You sell electricity, and it's very famous in Norway. What else? So in Brazil, Nissan was developing a car. I don't remember the name of the car, but it's interesting to see, for example, a video if you put solid oxide fuel cell Nissan Brazil. They wanted to build a fuel cell car run by ethanol. So you have ethanol that we have in Brazil. Every petrol station in Brazil has ethanol. You fill up with ethanol your tank, and this ethanol passes through the oxide fuel cell, which separates the hydrogen, and steam reforms happens within the fuel cell, produces electricity at a higher efficiency. So of course, why would you want to use a fuel cell instead of burning in an internal combustion engine? Because it's more efficient. So efficiencies are around 50%. If you want to burn ethanol, the efficiency is 25%, maybe even less than 25%. So this didn't work very well because these fuel cells, they operate at temperatures around 700, 800 degrees. So in a car, which is very small, it was difficult to insulate the heat coming from these cells. Nowadays, you have vacuum plates, which is extremely efficient for heat insulation, but still very challenging. Very challenging. Build a new car. Who's going to use? Only Brazilians. Well, I'm not going to invest in this technology. I'm going to invest in something that I make money out of. If Brazil, for example, decides into building a more efficient ethanol engine, they can use solid oxide fuel cell. So this cell, it's the electrolyte is a stria stabilized zirconia. So it's a ceramic, which is a mixture of zirconia and stria. And the cathode, the anodes are also ceramics. I don't know why they don't. They're probably different type of ceramics that work and have different efficiencies. They don't want to release whichever ceramics they use. So here we have another comparison, more with a table, easier to follow. So the operating temperature of proton exchange membranes, 80 degrees, solid oxide, 750. Proton exchange membranes take seconds, so you can drive a car really quickly. Sports car, solid oxide takes longer, so it's going to be a car that you accelerate and takes some time. Maybe what you can do, you can put a battery pack in order to give you the power for acceleration. And when you reach a certain speed, you run the oxide fuel cell and recharge your battery and provide power. Of course, you can always find a solution, right, for the challenges that you have, whichever technology you use. Power density, it's heavier, no, it's lighter, so you have a higher power for the amount of weight that you carry than oxide fuel cells. So oxide fuel cells are heavier, half the weight, the double the weight, or even 10 times the weight, depending on the fuel cell that you use. Overall efficiency 40%, oxide fuel cell 50%. This is for car, right? So if you use for ships and bigger transports modes, this efficiency increase. This also increases this efficiency here. Operating range 600 to 800 kilometers, 800 to 1,000 kilometers, mainly probably because of the higher efficiency. So with higher efficiency, you need less fuel in order to drive. Power system targets, the cost. So the cost of proton exchange membrane is high, is lower, it's cheaper. Solid oxide is more expensive. This one requires a cooling system to keep the fuel cell cool, which also adds weight to the system. But oxide fuel cell doesn't. Actually, you have to recycle the heat in order to make it increase the efficiency. You need to increase the temperature in order for the oxygen to be able to pass through the ceramics. Here the electric system is complex. Here is simple. The fuel, you can use hydrogen, and for oxide fuel cell you can use hydrogen, ammonia, ethanol, methane, diesel, gasoline, and other hydrocarbons. The target lifetime 800 hours, like 8,000 hours, 5,000 hours. So these are the type of uses. So cars, trucks, buses, ships. Sorry, I don't know how to say lunch in English. I never drove a Lancia in Europe. Do you guys know how to say Lancia? Anyway, so solid oxide fuel cells for big ships. This is GDGVs is Zeppelins, airships. Cogeneration. So for electricity generation, you only think about oxide fuel cells. You would only use proton exchange membrane if you want very low capacity factors, because the cost is low. If you want to just use for storage of wind and solar power, even that the cost is lower, you use proton exchange membrane, but it has a lower efficiency. But if you have, for example, if you want to store energy continuously, not varying so much, with a higher capacity factor of 50, 40%, then you use this solid oxide fuel cell. So the solid oxide fuel cell is very convenient also for carbon capture storage, as I mentioned, because when the fuel, as I mentioned here, the oxygen passes through the cell, so that the nitrogen stays out of the flue gases. So then it's much easier to separate water and CO2 than CO2 and nitrogen. CO2 and nitrogen is very complicated to separate. The cost is very expensive. So this is a very good technology for carbon capture storage. Looking at the volume and weight, for example, nowadays we have a very thriving industry for natural gas. So this is liquid natural gas, one tanker of 50 tons with the same volume, you can carry only, so to carry the same volume of natural gas, you need two tanks to carry liquid hydrogen. Carry liquid hydrogen, you need two cargo tanks, and the weight of both of them adds up to 20 tons. So you have to double the volume, but the weight reduces to the half, which is convenient for energy efficiency because you need to carry less cargo, but you have to invest more money in bigger ships, which will cost higher. The investment costs are higher, but operational costs are smaller. Of course, it takes a lot more energy to liquefy hydrogen than liquefy natural gas. Much more energy. But we're talking here about transporting the liquid hydrogen already in a liquid form. Liquid natural gas compared to ammonia, you also need two tanks with ammonia, but this ammonia will be much heavier than the liquid natural gas. So you're going to have to need much more fuel in order to transport ammonia. Sorry, I didn't put here ammonia. Ammonia. There are other approaches to transport hydrogen. So in this slide I showed liquid nitrogen, liquid hydrogen, or ammonia. There's also, for example, different components that you can form. For example, if you want to transport hydrogen from this location to this location, you would hydrogenate toluene and transform into methyl cyclohexane. And it's convenient because you need energy, you need to input energy in order for this reaction to happen. Why is good? Because you're selling energy. So it's supposed that in the location that you are, you have a lot of energy. Energy is cheap. You use energy to produce this, and then when you sell, you generate heat, which can then be turned into electricity with a steam turbine. And then you have your hydrogen, and then you produce toluene in the other side of the world where you sell your hydrogen. The only problem is that you don't only carry hydrogen, you also carry toluene, and it turns out that it's equivalent to carrying wood. So if you want to transport wood to burn, for example, you sell wood in Brazil to burn in Europe, it's expensive because wood is heavy and the energy density of wood is low. So you have to spend a lot of energy in the transportation in order to carry to the other side of the world. So transporting hydrogen is one of the highest challenges for the hydrogen industry because it's very difficult to pressurize, it's very difficult to liquefy, costs a lot of money, you waste a lot of energy doing this. So nowadays, a lot of people around the world are trying to think how to transport hydrogen very cheaply. I am one of these people, actually. I published a paper in energy conversion management, which is entitled Using the Jet Stream for Sustainable Airship and Balloon Transportation of Cargo and Hydrogen. So hydrogen is a lighter than air gas. My suggestion in this paper is to fill up very large balloons and let it fly in the atmosphere, and then the winds from the jet stream, which usually happens in these sections of the world around 30 degrees latitude and minus 30 degrees latitude, that reaches average the speeds of 150 kilometers per hour, so very high speeds, and they are very constant. Why they're constant? Because not sure if it's very relevant. We still have a lot of time. So why does this jet streams happen? You have very cold weather in the North Pole, in the South Pole, and what happens is that in the temperature in the equator is higher, much higher, and when the high temperature of the equator reaches the North Pole, it rises. And when you rise in the atmosphere, what happens is that the pressure of the atmosphere reduces. So if you have the Lavoisier equation, you have pressure is equal to volume divided by temperature. In this case, the volume, the pressure reduces, the volume increases. So what happens is that the more air has to flow in order to meet the energy balance. Because if there is, for example, one meter cubic of air rising, and then what happens is that it's pushing from below, but then the pressure up there is very low, the speed increases a lot. So what happens is that if you have the wind speeds at lower altitudes, is going to be multiplied by 10 or 20 on the close to the stratosphere. So on the top of the troposphere to the stratosphere, the pressure is very low. But so, for example, there was one person which managed to fly around the world with a balloon. So there is a sport called ballooning, and people try to cross the world with balloons. And they have a helium cell, which is heat up with hot air. So they take both benefits of the helium, which is lighter than the air. They're not going to use hydrogen because it can blow up because they are heating up on the bottom, and the temperature difference. So then they can control the altitude of the balloon by increasing or reducing the temperature of the balloon. And they managed to go around the world in the southern hemisphere because it's much more convenient to travel on the southern hemisphere using the jet stream because it's much stronger than the northern hemisphere. So he went around the world in 11 days, and he managed to land. This is the incredible thing. He managed to land something like 100 kilometers away from the location where he started. And this is only by increasing and lowering the altitude of the airship, because at different altitudes of the atmosphere, you have different prevailing winds at different directions. So you have to have very good computation models to know at which altitude, at which time you need to travel in order to reach the final destination. But this guy is very good, and he knows, and then he managed to break the world record just by heating up a balloon. Well, the main disadvantages of this technology is because hydrogen is too light, and what happens is that when you throw a lot of hydrogen in a balloon, the problem is to bringing it down, bringing it back. But we have several advantages, with this. For example, we can mix with ammonia, and ammonia liquefies at around -70 degrees, which is the temperature of the stratosphere. So, for example, when it reaches 10 kilometers, 15 kilometers high, the balloon will stop rising because the ammonia will liquefy, so reaching an equilibrium at that height. And also, if you burn hydrogen, what happens is that you produce water, and 1 ton of hydrogen produces 9 tons of water. So you can run fuel cells to compress the hydrogen, and you also condense the water, so increase the weight of your balloon. And it turns out that you only lose 10% of the efficiency transporting hydrogen with a balloon. If you use liquefied if you liquefy hydrogen, you have to consume something like 35% of the hydrogen that you are transporting. So now we talk about transporting hydrogen. Now we're going to talk about the global experience of hydrogen. Hydrogen is already a thing in Japan. So there's a lot of investments in companies developing every type of different applications with hydrogen, and the future is hydrogen. In Japan is always in the future, and they already have several solutions. If you know how to speak right in Japanese, and you look in Japan for hydrogen solutions, you'll probably find anything that you can think of. One of the reasons why Japan is so focused on technology advantage, technology innovation, is because they don't have natural resources and they need to sell patents, they need to sell technologies. And if they stop innovating, what happens is it's going to become a very poor country, because they don't have the influence that the US, that Europe, the UK has, or all the other countries, in order to manipulate their commodities. And, you know, the way that the US makes money, England makes money, Japan doesn't have this influence. So, the only way that they have in order to remain a competitive country, they have to innovate. And they know this very well, and they're doing it at the moment. So closing up this this thing of hydrogen and oil and gas industry. So the oil and gas industry realized that hydrogen is the future. In order to maintain them working, maintaining the oil and gas industry existing, they have to invest in hydrogen, because a lot of countries are investing in sustainable solutions. Hydrogen is a sustainable solution. Let's invest in hydrogen. And from 2020, you have that the highest increase in investment in oil companies was hydrogen, which multiplied by 100% compared to from 2019 to 2020. So, for example, if you want to do a project now, research and development project, and you have a hydrogen project, the likelihood that you get finance is high, because everyone wants to invest in hydrogen today. So talking about the hydrogen consumption, nowadays energy is supplied by fossil fuels, and gas supplies around the world on average 40% for heating and cooling, 30% for industry, for example, steel industry, cement, concrete is cement, sorry. Power, so power generation, 30%. Oil is transport sector, air industry, shipping industry, petrochemicals, building and power. So, for example, diesel, supply electricity in the houses of people's houses. So this is the share of how much energy is consumed around the world with gas and oil. And hydrogen can replace all of them but one of these solutions. And I want to ask you, which of these solutions it will be the most difficult? I mean, maybe they can't exchange all of these. For example, in industry, probably a challenge. Anyone want to guess? Right, so the one that's it's very difficult to change is petrochemical. And the reason why is because hydrogen doesn't have carbon. And in a petrochemical, you need to create molecules, plastics, and several other pharmaceuticals and things which have carbon. And hydrogen is the only fuel that doesn't have carbon. I mean, there are other fuels, but the only major fuel which doesn't have carbon. So this one will be very difficult. I mean, I would say impossible to provide with hydrogen. You have to find, for example, biomass, recycling, another solution in order to supply the petrochemical industries, because hydrogen can't, because it doesn't have carbon. So, but almost everything, right? So it can do a lot of things, which is great. How do you produce hydrogen? You have in this slide 5 different colors, which means 5 different approaches. The first one is the green hydrogen, which basically you use renewable energies, nuclear energy. You run through energy technologies, electricity generation technologies that does not produce CO2. You run through electrolysis of fuel cell, not fuel cell, electrolysis, and then you produce green hydrogen. And this is very convenient because hydrogen industry needs renewables, right? But the renewable industry also needs hydrogen because it's intermittent, it's variable. You can't rely on it. So hydrogen will come as also, apart from all the things that I've been talking here, for an energy storage solution for renewables. So it's a win-win for hydrogen and renewables. It's great. The other solution is using fossil fuels. You can use natural gas to pass through the steam methane reforming process and produce gray hydrogen. Steam with methane reforming produce around 95% of the hydrogen today in the world. And it's all gray hydrogen, but the demand is not extremely high, for example, as methane demand. It's very tiny. It's only for certain industry, petrochemical demands. And you also can use coal. You gasify coal, you produce syngas at high temperatures, low CO2 concentrations. You produce syngas. So steam reforming, I didn't explain how steam reforming works. Steam reforming, you have methane with steam, very high temperatures, very high pressures, and then the steam reacts with methane, producing CO2 and hydrogen. As simple as that, but it's energy consuming. Of course, you lose a lot of the energy that you have in methane. And it doesn't really make any sense to produce hydrogen instead of using methane. If you're using this process, you might as well use methane instead of hydrogen, because you lose a lot of energy in this process, and hydrogen is difficult to manage. It takes a lot of energy to pressurize, it occupies huge volumes, and it's difficult to manage. So then in order to make this acceptable in a sustainable approach, you would have to capture and store the CO2 that you produce by producing the hydrogen. So, for example, you can run this steam methane reforming, as I explained, with a solid oxide fuel cell, and then you can easily store the CO2. Not easily, you can easily capture the CO2, but then store is more complicated because you have to find a location on the ground that's appropriate for you to insert and store and close it and pray that it's going to stay there for millions of years. Yeah, so this is blue hydrogen. Then you produce blue hydrogen. It's natural gas with carbon capture storage. Then you have coal, which is gasification. How gasification works, you put, for example, coal in a gasifier, and which is a very high temperature reactor with very controlled amount of oxygen coming inside, which maintains the temperature very high. At very high temperature, coal turns into hydrogen, methane. If you control the amount of oxygen and temperature and pressure, you produce more hydrogen, and then you can separate this hydrogen and produce brown hydrogen, which is really bad. But then if you capture and store the hydrogen, then you produce blue hydrogen. Well, in the gasification, you produce methane. Also, you can also use the methane. You can also have a steam methane reforming process after the gasification to produce more hydrogen, but you would still be brown hydrogen. So this is kind of the life cycle. You have fossil fuels, biomass coming in. You gasify, you store the CO2 ground, you clean hydrogen, compress, and then you sell for you distribute for your appliances. Or either you can liquefy and then transport in tankers or ships for far away. These are the other ones: electricity, electrolysis. Electricity, of course, you don't even, if you can use electricity, you don't need to turn into hydrogen. You just use as electricity. Right, so these are the types of hydrogen produced now. Europe has a lot of money to invest in hydrogen, and this is the plan. This is their plan for investing in hydrogen in the next 30, 40 years. Basically, they are going to start producing hydrogen from natural gas, very inefficient, very expensive, very bad way of producing hydrogen, which increases actually CO2 emissions maybe 2 or 3 times. But this is just a way in order that oil and gas industries continue producing gas. Of course, they still make money with their oil fields, but at the same time, you create markets for hydrogen appliances. So hydrogen stations will come up, and people start driving hydrogen cars, and other appliances for hydrogen solutions will become viable, and they'll come to the market. So they will pay this price of polluting the environment just to kickstart an economy with hydrogen. And then after, they will replace this gray hydrogen, which is produced from natural gas, with blue hydrogen, which is natural gas with carbon capture storage. And they are very optimistic about this. I personally don't think that it's very easy to store the CO2. So maybe this is not going to be possible. Probably what they're doing, they're just saying, okay, we're going to store in 5 years' time, we're going to start storing. And then after 5 years, they say, oh, in 5 years. And then after 5 years, in 5 years. It's very complicated to capture and store CO2. There are very, very little projects ongoing now. There are some investments on this technology, but people talk about carbon capture storage for like 15 years, and it has never become a thing. But then the idea is eventually hydrogen will be produced with renewable energy sources and electrolysis, and then it will replace blue hydrogen. And then you also have this biomass, which is what Ufan was mentioning. You can produce hydrogen with biodegradation, depending on the factories that you select, depending on the temperature, concentrations, pH. You can produce hydrogen from biodegradation or biomass. You can gasify biomass and also store the CO2 afterwards. So storing CO2 from biomass is interesting because you reduce the CO2 that you have in the atmosphere. For example, you have 400 ppm of CO2 concentration in the atmosphere. You can reach 350, 300 if you use biomass in CCS, because you catch the CO2 with the trees, you burn, and then you get the CO2 and you put it back on the ground where it came from. So this is the plan, European plan. So now I talked about production of hydrogen. Oh no, so there's another way of producing hydrogen, which is not mainstream, but is gaining a lot of attention. So there's a very interesting publication, 2020, so this year, showing all the hydrogen, natural hydrogen reserves around the world. So basically, we nowadays use natural gas, which is methane extracted from the ground. There's a lot of sources of hydrogen in the ground, which you can store similarly to natural gas. For example, this hydrogen can be produced with the biodegradation of dinosaurs, of plants, algae in the past. So some of the production wells, so some petrochemical industries, they have to burn hydrogen because it's not viable to sell it nowadays. Something like 10%, 15% of hydrogen that they produce in their extraction wells. So there is also, so this is one source of hydrogen, natural hydrogen mixed with gas and oil. There's also different other types of hydrogen on the floor, which are formed by, for example, seawater entering into connecting into a crust of a geological crust, which oxidizes the material, and oxidation, what happens at the oxygen oxides the minerals, and then the hydrogen comes out. There's hydrogen, so there are several layers of geological layers full of hydrogen, and you could literally create a well, like an unconventional well, which you drill a pipe and then you extract, similarly to natural gas, you can extract natural hydrogen. This paper mentions that there is around 4 times more natural hydrogen than natural gas around the world. So it's a big business, right? People should start, oil companies are already investing in this. I'm gonna give you one example. And the future of natural hydrogen is just starting. People are talking about this now. Let's see. Half an hour. There is another very interesting concept that I want to share with you, which is another issue that a hydrogen economy results. Because, for example, if you take water from the ocean and you use electrolysis and you burn hydrogen, you produce water. But the problem is that if you don't burn the hydrogen and it escapes to the atmosphere, what's going to happen is that it's going to rise very quickly up to the thermosphere. And then at the thermosphere, at something like 10,000 kilometers high, 100 kilometers high. So from 50 kilometers high to 100 to 500 kilometers high, you have the thermosphere, and there's no molecules there. So, for example, hydrogen molecule becomes atoms, ions, and they also meet with oxygen ions, and they merge and produce water. So some of this hydrogen comes back to the Earth as form of water. But a lot of this hydrogen that reaches the thermosphere escapes the Earth atmosphere. So there is a problem that if we produce a lot of hydrogen and we use the hydrogen and increases the leakage of hydrogen from the crust of the Earth, what's happening is that you're going to reduce the amount of water that you have on the Earth. So the sea levels will eventually start to reduce because you are consuming the water, and the CO2 escapes the atmosphere, the oxygen stays in the atmosphere because it's much heavier. So